So in our last topic of the quarter, which will be essentially atomic spectra, but in order to understand atomic spectra, and actually the atomic spectra that you've been looking at all quarter, we have to do a little bit of a side trip into quantum mechanics. And why not make it as dusty and boring as possible and actually take a trip through the physics or the history of physics entirely? There actually is this kind of watershed moment right at the year 1900, where basically people had thought that they had figured all of physics out. And there were these three theories that basically described in its entirety the world around them, with a couple of notable exceptions. There was Newtonian mechanics, so you could predict the motions of stars or planets and asteroids and comets to exquisite precision. There was the electromagnetic theory that not only explained light, and that's what we've talked about a lot in this class, but was also being used to create these technological marvels like radio and the telegraph. And then there was thermal physics, which was also being used to figure out or create these incredible machines like steam engines that were, kind of taming travel. And on the less exciting side, predict the fact that the Earth was, I think, like 20 million years old. So this guy in the picture, Lord Kelvin, did that. He wasn't right. And the underpinnings of these theories, so it turns out that nobody thought enough about how incompatible these were, but this will be important in a couple of minutes. So Newtonian mechanics is essentially a theory of particles. And this goes all the way back to the ancient Greeks, where if you have a lump of gold, for instance, I beat out the lump of gold into a sheet, I cut it in half, I beat that sheet out, cut it in half, hammer it more, cut it in half, and I can keep doing this. That sheet of gold is still gold until I get to a single atom. And then that single atom of gold, I cannot cut that in half and have it still be gold. If I cut that in half, I get something else, depending on what the daughter nuclei are. But this is what finitely divisible means. At some point, it stops. There is a fundamental unit of whatever that matter is, an electron, a proton, a nitrogen molecule, whatever it is. So that's really the theory of mechanics, the theory of matter. However, the electromagnetic theory, there's no limit to the cutting in half. So if I have a light wave, a classical wave, I can cut it in half and cut it in half. And you could imagine doing this with the things that we used in class, polarizers. So I could have just a polarizer at a 45-degree angle with another polarizer, and then a third and a fourth and a fifth. And in principle, in the theory of electromagnetism that you guys learned, there's no end to that. I could have the smallest possible amplitude electromagnetic wave. This is infinitely divisible. So at no point do I actually completely extinguish the wave with even an infinite number of polarizers. Contrasting that to taking, my sheet of gold and cutting it in half, and at some point it stops. And then there's this theory of thermal physics, which kind of connects the two, where I have individual atoms and molecules, and I wiggle them, and they emit electromagnetic radiation. And in some sense, thermal physics is infinitely divisible too, because if you think about, for instance, the Maxwell-Boltzmann distribution, I could take a particle in that, an atom, and I could just nudge it a little bit faster than it's going. So there's no limit to the precision with which I could give a molecule some velocity and therefore some kinetic energy. So I've got some of these theories acting on finitely divisible matter, some of them acting on infinitely divisible energy. Turns out that's going to be a big problem. And the first hint that that was a big problem actually came in this, what was kind of a victory lap. Again, in 1900, these guys, so this is Lord Kelvin in this Old Testament prophet-looking picture, they thought they'd basically figured everything out, and physics was really boring. And so the speech, which was essentially saying, we're done, this famous Lord Kelvin speech, pointed out that there were two problems, only two little clouds that they had to deal with. And those two little clouds were the fact that the speed of light is constant in any reference frame, and a little problem with the thermal spectra of hot objects. So the fact that the speed of light is constant, I'll just mention what that problem is, not what we'll talk about in this class. This is basically what gets you to relativity, and then those ideas to general relativity. But the idea is that if I'm standing there and I fire a laser pointer, shoot a laser pointer, the light leaves the laser pointer at the speed of light, so c. But then imagine that somebody's whizzing by me on a rocket that's going at half the speed of light and they shoot a laser pointer. So naively, you would expect in Galilean relativity that that laser pointer, from my point of view, would be going at 1.5 times the speed of light. Within the equations of electromagnetism, Maxwell's equations, that is just not supported. So no matter what reference frame you're in, it seems like light moves at the speed of light. And what has to be sacrificed in order to keep the constancy of the speed of light is our notions of space and time. So that turned out to be a bigger cloud than Kelvin thought. The other cloud, in his two-cloud speech, is the thermal spectra of hot objects. And this has to do with the infinite divisibility of electromagnetic energy. So I've got a hot object, the molecules are jiggling, the jiggling molecules are emitting light. If you count out the ways that the molecules and solid can jiggle, what you realize is that it's easy to make, there are more ways of making small wavelength light than there are big wavelength light. So it's easy to, for instance, just nudge a molecule and have it move a little bit. And it's easier still to make the energy produced by that wiggle be a tiny amount of energy. And if you start adding everything up, what you realize is what they called the ultraviolet catastrophe, is that all of the energy in a solid that's radiating energy in the form of light should be in really, really, really tiny wavelength light. And because there are a lot of ways of making a small amount of light, the whole thing should basically immediately give up all of its energy in the form of X-rays. That's not good. So absolutely not observed. So this is what Kelvin was talking about with his second cloud. Turns out that a lot more clouds were on the way, and it turns out all of these clouds are related, and they lead you to quantum mechanics. So cloud 3 is the spectra of elements. We won't get into it because we've been talking about this a lot all quarter, is basically like what's going on with these lines. Why do these lines show up at certain specific wavelengths when I would imagine that I could just, jiggle an atom and have it produce any type of wavelength that I wanted? So essentially, this is like a slightly more precise issue, way of phrasing the issue that was noticed in the thermal spectra of hot objects, is that light doesn't seem to come out of matter in any sensible way. And things got even weirder when people started investigating the nature of the atom itself. So first, what we now know to be electrons were isolated from what were then called cathode ray tubes. If you have a really, really, really old monitor or TV, those are actually cathode ray tubes. They produce a beam of electrons that splatter on the screen. So these things were isolated. It was found that they respond to electromagnetic fields. So it turns out they have charge. And the charge is the charge of the electron. A second experiment, the Millikan oil drop experiment, which kind of historically turns out that his data wasn't particularly amazing and he may have fudged it. But basically, he squirted ionized oil droplets into this weird can-looking thing that had charged metal plates. And what he noticed is that the drops of oil would actually isolate themselves in bands. And now we know that what's going on with these bands is that the bands are indicative of having one missing electron, two missing electrons, three missing electrons. So in between the cathode ray tube experiments and Millikan's oil drop experiments, what people were able to realize is that you can just pull these things out of matter. They're chunky, they're particles. So this is one electron, two electron, three electron. Therefore, what atoms must be made out of is some sort of positive background and then these electrons stuck inside of it. And they've got to be stationary because if I move them around, they would emit light. So this is what was called the plum pudding model, because I think this guy's English, and they have all sorts of gross puddings, where there's this kind of positive ectoplasmic goo and negatively charged electrons so that the whole thing is net neutral. So it turns out that that is absolutely wrong too. And if you take a sheet of gold, in this diagram it's platinum, but I think the first experiment was gold. So you take a really thin sheet of gold and then you fire alpha particles, another recently identified type of radiation. An alpha particle is basically a helium nucleus, two neutrons and two protons. So you fire the alpha particles at this sheet of gold. You would expect in the plum pudding model, because the alpha particle is about 8,000 times the mass of the electron, it would just go right through them. So everything at spot one. What they discovered in this experiment, and I don't know who said this, I think it was Rutherford, the experimenter, it could have been Zeeman, the kind of theory guy, is that they bounced back. A lot of them bounced right back. And if you think about the relative masses, one of them said it like this, it was as if we fired a piece of heavy artillery at a piece of paper and the shell bounced right back in our faces instead of going through. So really kind of astonishing. So you'd get these gold foil collisions that indicated that there was something big and dense and heavy somewhere in the gold foil. Of course, that's the nucleus now. This was them figuring it out. And this indicates that there's sort of a planetary model of the atom, where there's a big, heavy, positively charged thingy, and it's surrounded by these smaller, about 1/1800th of the mass sized particle. And everything kind of makes sense for one brief moment where, okay, fine, you've got this heavy, positively charged nucleus. I've got these negatively charged electrons. If I have a neutral atom, I've got maybe 10 positively charged protons and exactly 10 negatively charged electrons. The distribution of electrons can explain a lot of chemical phenomenon. This is actually really great, right? And I know that because opposites attract, the electrons are attracted to the positively charged nucleus, and so maybe they're orbiting in the same way that planets orbit the sun. There is a huge problem with this. But remember that conceptual picture, because that's how we're going to define the Bohr model, is that the whole point of making radiation by wiggling matter is that when I wiggle matter, it makes radiation. And if you think about something in orbit, in this case, the electron in orbit around the proton, it's wiggling. It's wiggling in both the x and the y direction, in fact. And the radiation that it emits as it does this would fly out into space, energy is conserved, so it would lose that energy, and it would spiral into the center of the proton, or the center of the nucleus. And if you actually work out the theory of radiating matter in this way, you would get that all of the atoms in the entire universe would actually radiate away all of their all their energy in this fashion in less than 1/10 of 1/1000th of 1 second. So this planetary model, as it stands now, cannot possibly be right. It is the wrongest thing that you could possibly imagine, because I look out into the universe and I don't see everything collapsing in 1/10 of 1/1000th of 1 second. So here we are, it's a few years later, and these two little clouds basically turned into a, like F5 tornado. So basically, imagine for a second that you're these, kind of old dude physicists, and you basically thought that you were done and you had figured out all of physics, and basically the whole thing just kind of blows apart in your face over the course of 15 years. It's just this sinking feeling that, the whole edifice on which you founded your career and your life was kind of like crumbling. The good news is out of this complete wreckage, the theory of quantum mechanics sprang into existence, which is incredibly successful, incredibly useful. We won't get into the details of it, obviously, because that's, a upper level physics class in and of itself. But what really is going on is this deeply conceptual philosophical issue about finitely versus infinitely divisible stuff, and trying to weld those two theories together. It doesn't work. And this is where all of these catastrophes come from. So what's really true is that, in a weird way, there wasn't a decision to be made, is that nature in some circumstances treats electromagnetic radiation, light that is, like it's a particle, and in certain circumstances it treats matter, like electrons, protons, nitrogen atoms, like a wave. And it does so in such a way that the theory of matter and light is kind of unified. They're neither waves nor particles, or in certain circumstances they act like either. And now they can kind of interact coherently. But again, quantum mechanics is not something we're going to cover in a 10-minute video. So what this does do is this kind of vindicates this 1,000-year argument about whether or not light is made of particles or waves. The answer is that it's actually both. And the side note to that is, and somebody actually pointed this out, a mathematician named David Hilbert said, like, you know how geometric optics kind of says light acts like particles until you look really close and then it's a wave? What if that's true about matter too? And that was in like 1848, 50 years before this. So it turns out that the missing piece is that we haven't talked about how matter acts like waves. And we'll do this in the smallest way possible. We'll just talk about the de Broglie wavelength and the Bohr model of the atom. So let's say I had a beam of electrons, and you would imagine this as like a whole bunch of lumps of stuff, little probably green balls going through a double slit experiment. Like the double slit experiment we performed and talked about using light, not electrons. It turns out what you would see and what people absolutely do see is that the electrons show up with an interference pattern. So interference, wave interference, is obviously a wave phenomenon. And the crazy thing about this is if you turn your beam of electrons down until it's only one at a time, you still see an interference pattern. So in some sense, each electron has its own personal, what's called a wave function, and each electron goes through both slits, and each electron interferes with itself and knows to not show up in the dark spots, only show up in the bright spots. So that's where we get into a little bit of the weird weeds of measurement theory. But the point is that matter has a wave-like nature. And what we need to know minimally about the wave-like nature of matter is that there is a wavelength, and that wavelength is given by the de Broglie formula. So the wavelength of something like an electron, a proton, an atom, a baseball, it would be super teeny tiny. The largest visible quantum mechanical thing where you can actually see its wave nature are these things called Bose condensates. So you can get about 250,000 atoms to act like a wave. They've got to be the exact same atom, and they've got to be basically at absolute zero. But this is the wavelength of matter, not light, matter. So it's given by h, a new constant called the Planck's constant. This is basically the fundamental constant of quantum mechanics, in the same way that big G is the fundamental constant of gravity, and epsilon naught is the fundamental constant of electric fields. So Planck's constant in SI units, it's 6.626 times 10 to the minus 34th joule seconds, or I personally prefer joules per hertz, and then divided by p. P is the momentum, MV straight out of mechanics class. So the bigger momentum you have, the smaller your wavelength. This is why we don't see matter acting wavy in the regular world. So Planck's constant is tiny, and the masses that we're used to dealing with is huge. But for something like electron, and we'll do some calculations in the next video, you actually notice this. So the second thing you have to realize is that waves have standing wave behavior. So if matter acts like a wave, and I put an electron, for instance, in a big square well, so it can't go farther left than some point, and it can't go farther right than another point, what it'll do is exactly what you guys may have seen in a standing wave demonstration or experiment. So it'll make standing waves. And in some sense, what you're seeing in these atomic spectra is, if you play a stringed instrument, percussive like a piano or violin, or bowed like a violin, is that the reason there are these specific tones is because you've got the wave going through the string bound at both ends. In the case of the guitar, at the nut and at the tuning pegs. So by constraining a wave to only make standing waves, what you end up with is only precise certain tones. So this is basically what's going on in an atom, is that the electron, which is described by a wave, because forgive me for saying this if you know more about quantum mechanics, because it's quote-unquote traveling in a circle, and it's got to end up back where it started. So it's only allowed to have, just like a standing wave in a guitar string, one antinode, two antinodes, three antinodes, four antinodes. There are only certain allowed frequencies or wavelengths that it can be constrained to. So this is essentially the atomic spectra. It's kind of like the music of the atom. And an electron can only be in one or a different specific so-called orbital. And this leads to only certain allowed changes in energy, and therefore types of light coming out. So these are the details we'll get through when we talk about the Bohr atom, which is a really great approximation for hydrogen. Doesn't work so great for anything else. Well, almost anything else. And it'll essentially showcase like characteristic quantum behavior for us, and it does a really good job of explaining the hydrogen spectrum. But this is basically hydrogen light, so take some hydrogen, put it in a lamp, beat it up with electricity. It'll make kind of a purplish color, break that light up into a prism. These are the only wavelengths of light you'll see. And the reason you only see these wavelengths of light is because there are only certain allowed ways that the wave that describes the electron surrounding the proton in the hydrogen atom can configure itself. And then finally, what you have is the mystery of, for instance, stellar spectra. So this is the showcasing of two different types of behavior. So what's going on in the interior of the star is non-quantum mechanical stuff. Basically, there's this really hot plasma in solids or liquids or plasma. The atoms are so strongly interacting, you don't actually see this kind of delicate, almost musical quantum mechanical behavior. And then you see these emission line or absorption lines located at, for instance, here and here. I think this is the infamous hydrogen alpha line. So these are cooler gas located in the exterior of the star, and they've got to be gas, and the gas is actually doing this quantum mechanical stuff where it only emits only absorbs its favorite wavelengths of light. And you guys found and analyzed that, I think, in Project 5. The background is definitely non-quantum. So this is what's called a thermal blackbody spectrum, and that's basically the chaotic light coming from bulk matter. So to abuse my musical analogy, I'll say it this way, is that there are two types of ways of making an orchestra, the instruments in an orchestra make noise. You could play them. They'll produce only certain tones. That's quantum mechanics. Or you could throw them off a cliff. So that's the light produced by thermal agitation. So what we'll do again is we'll concentrate on just the Bohr model of the atom to showcase the concepts of the Broglie wavelength and show why energy levels are quantized. And quantum mechanics itself is a huge field that we obviously will barely even scrape the surface of.